My name is Wick Haxton. I'm the Physics Department Chair. It's my honor to welcome you to the 22nd Annual J. Robert Oppenheimer Lecture. The Oppenheimer series was established in 1998 with the main support by a gift from Steve and Arlene Krieger. The series has brought a who's who of theoretical physics to Berkeley, including C.N. Yang, Freeman Dyson, Frank Wilczek, Gerard 't Hooft, Robert Laughlin, Ed Witten, Stephen Hawking, Claude Cohen-Tanucci, Murray Gell-Mann, Kip Thorne, last year's speaker, Michael Turner, and our own Marvin Cohen from Berkeley, who is actually in the second row tonight. Robert Oppenheimer was born in 1904, growing up in an upper-class family in Manhattan. He graduated from Harvard, majoring in chemistry, entered Cambridge University in 1924 as a graduate student in the hope of working with Ernest Rutherford, then leaving in 1926 to finish his PhD with Max Born in Göttingen. He published more than a dozen papers while with Born, mostly focused on the new theory of quantum mechanics. This included his most famous paper on the Born-Oppenheimer approximation that simplifies molecular motion by separating the slow nuclear motion from that of the faster electrons. 90 years ago, in 1929, after 2 years of postdoctoral study, Oppenheimer came to the US, returned to the US and to Berkeley. He accepted an associate professorship from us, and he remained here for 15 years. During this period, he published his most famous paper with Volkoff, establishing the Tolman-Oppenheimer-Volkoff limit on the maximum mass of a neutron star, the mass above which the star must collapse into a black hole. He also developed a theory of that collapse and black hole formation. Both topics today are of keen interest with the recent observation of gravitational waves from black hole and neutron star mergers. At Berkeley, the Oppenheimer group, which was typically 8 to 10 graduate students and a half a dozen postdocs, met with Oppie every day, with Oppenheimer probing them on their progress. Hans Bethe noted that probably the most important ingredient he brought to his teaching was his exquisite taste. He always knew what were the important problems. The scientific leadership that Oppenheimer demonstrated at Berkeley actually complicated his life later on and affected his role in science. In 1942, he was selected to lead World War II's Manhattan Project, the engineering site located at Los Alamos, New Mexico, which was near a ranch that Oppie owned. His leadership of this effort culminated in the successful Trinity test and later to the political decision to use atomic weapons against Japan. This decision troubled Oppenheimer for the rest of his life. After World War II, Oppenheimer became the public face of science and technology. In his day, the analog of Carl Sagan. He was featured on covers of Time and Life magazines. This period of his life effectively came to a close with the controversial loss of his security clearance in 1954, a time when new Cold War and McCarthyism were stoking many fears. Some resolution occurred a decade later when President Kennedy selected Oppenheimer to receive the nation's Fermi Award. Oppenheimer's legacy at Berkeley is summarized by a plaque on the 4th floor of Old LeConte with another quote from Hans Bethe, and the plaque's right here. In these corner offices from 1929 to 1942, J. Robert Oppenheimer created the greatest school of theoretical physics the world has ever known. Berkeley physics really strives to continue his legacy today. It is now my great pleasure to introduce my colleague Bob Kahn, senior scientist at Lawrence Berkeley Laboratory, and he will introduce tonight's Oppenheimer lecturer, Helen Quinn.
It is truly a great honor to introduce this year's Oppenheimer lecturer, Professor Helen Quinn. As I will briefly recount, Professor Quinn has made fundamental contributions to elementary particle physics. She has served as a leader of the physics community and has devoted herself for many years to the improvement of science education in the United States. For these achievements, she has received much well-deserved recognition. But for those of us who've been privileged to know her well, she represents much more than all this. She embodies the ideals to which scientists should aspire, not just excellence in research, but devotion to the larger community, great personal integrity, humility, and compassion. For this reason, I'm especially grateful for the opportunity to review a few of her many accomplishments. A native of Australia, Helen came to the United States partway through her undergraduate education, which she finished at a school about 50 miles south of us. She continued her graduate education there, receiving her PhD under the direction of the renowned theoretical physicist B.J. Bjorkane. Professor Quinn is the co-author of 2 papers that address the most fundamental questions in physical science. Together with Howard Georgi and Stephen Weinberg, she showed how the strong electromagnetic and weak interactions might evolve from a grand unified theory at high energy. With Roberto Pecce, in 1977, she proposed a solution to a puzzle involving CP violation. CP symmetry connects particles and antiparticles. For example, it says that if electrons emitted in radioactive decay spin clockwise, then positrons, anti-electrons, should be emitted spinning counterclockwise. Experimentally, we know that CP symmetry is violated. It isn't exactly true. But CP symmetry seems to be respected in strong interactions, the forces that bind neutrons and protons in the nucleus. There's no a priori reason that this should be so. This is the puzzle for which Professors Quinn and Pecce proposed an answer. CP violation is really important. Andrei Sakharov showed without CP violation, there wouldn't be any matter left in the universe. What is more, the Pecce-Quinn proposal may ultimately explain dark matter, the 80% of the matter that remains a complete mystery. Experiments continue today to look for the axion, a particle that would be a consequence of the Pecce-Quinn symmetry. Professor Quinn was a leader, too, in developing the program for investigating CP violation at the experiment called BABAR at the Stanford Linear Accelerator Center, an experiment in which both Berkeley and Stanford played central roles. After her PhD, Helen held a series of positions at the DESI Laboratory in Hamburg and at Harvard University before joining the staff at the Stanford Linear Accelerator Center in 1977. In 2000, she, together with Howard Georgi and Yogesh Pati, were awarded the Dirac Medal. She was elected to the National Academy of Sciences in 2003 and was subsequently made a professor at SLAC. She was the president of the American Physical Society in 2004. In 2008, she became the first woman to receive the Oscar Klein Medal from the Royal Swedish Academy of Sciences. In 2013, she received the J.J. Sakurai Prize from the American Physical Society together with Roberto Pecce. There are too many more awards to mention, but actually Professor Quinn is here to speak about her work in an entirely different domain, education. She was a founder of the Contemporary Physics Education Project, whose chart of the fundamental particles is ubiquitous. From 2009 to 2014, she was the chair of the Board of Science Education of the National Academy. She served on the National Research Council study that produced the report, Taking Science to School, and chaired the Committee on a Conceptual Framework for New K-12 Science Education Standards, which provided the basis for the next generation science standards. These and similar standards have now been adopted by about 30 states in the United States and have been influential internationally as well. Professor Quinn also contributed to a follow-up NRC study on the assessment and implementation of NGSS. From 2015 to 2018, Helen served at the request of the President of Ecuador as a member of the Commission Gestora to help plan and guide initial development of National University of Education of Ecuador. Professor Quinn tonight will present Teaching for Learning in K-12 Science and Physics at the University Level, what I have learned from learning research. She will share her insight into K-12 science and physics education in the U.S. Please join me in welcoming our distinguished speaker, Professor Helen Quinn.
Okay, so I took the liberty to change the title a little bit. And the title is about what you have to do to teach. You have to do science, you have to engineer the teaching situations, and then teaching itself is an art. So I'll talk more about that as we go along. I have to start by apologizing, because this is a lecture. This is a lecture about why you shouldn't give lectures. So clearly that's a mistake, but I think I can make it interesting enough. However, I also will leave my slides with somebody, and somebody's videoing the lecture. So anybody who's a teacher and wants to check back on some detail can do so later, because nobody can remember everything they hear in an hour when they walk out of the room. And that's part of the reason why giving lectures is a very inefficient way to teach. I'm coming here to talk about other people's work. Lots and lots of research goes into knowing how to teach. And it's research most scientists don't know much about. So what's there are actually the studies that were there before we began the work on the framework in K-12 science education, coming from the National Research Council. Any one of these things can be freely downloaded from the National Academy Press, which is the website given there. And the Board on Science Education is the organization that charters these studies, just as the Board on Physics and Astronomy charters studies to guide the future of physics and astronomy in this country. So it's a useful resource, and there's many things there. And I began to learn by participating in this study, Taking Science to School, what the research on learning has learned. Now, some of this we've known for a long time. One of the first people who really preached a different kind of science education was John Dewey. And the kind of science education we're talking about here is not so different from what he was saying. But his conclusions have been reinforced by many years of people doing a variety of kinds of research. Research on how the brain works, research on learning generically, and research specifically in science classrooms, particularly at the university level, on what works and what doesn't work, and for whom it works and doesn't work. And so this talk is based on a large base of information. These studies over here on the left are other useful documents from the National Academy having to do with education. They're not studies of research on learning, but they're issues that come up when you're teaching science, like creation and evolutionism, where it's useful to have a resource for teachers that say, these are the arguments that are used against evolution, and here's the way to refute that argument based on the evidence. So that's also other work that the Board on Science Education or the National Academy more broadly has done. So building my knowledge of this area is how I got into this, because when I became a member of the National Academy, Carl Wyman, who started the Board on Science Education, invited me to join simply because I'd been doing some work with teachers throughout my career, and not that many Academy members had. So I got involved, and I got more and more interested in how do we do this better, and then had the opportunity to take on the next study. The studies that are listed here are ones that I participated in, not the How People Learn 2, which is an update of the How People Learn, but these more recent studies continue to reinforce the direction I'm talking about. So it's not just my opinion, it's really something based on a rather large body of research that says teaching for most students needs to be different from the way we've been doing it. And I particularly focused on K-12, and we'll talk about that. But really, we have to think about it the same thing at the college level. And much of what I say for K-12 applies just as well for the college level. First of all, at K-12, we want all students to learn science. Why? Not because we want all students to become scientists, because they won't, but because we want citizens who are scientifically literate. We want citizens who know what it means to argue from evidence, or to evaluate a claim that's made based on what's the source of the claim and what other documents I can find say about this claim. How do you think through a problem and understand, decide whether to vaccinate your child or not, or decide what to vote about in the location of a power plant in your neighborhood. People need to be able to interpret scientific information in their lives, and if they haven't learned to do that in school, they're not going to do it well in life. And we unfortunately see evidence for our failure to teach them to do that in the world today. So, what's the teacher's role? The teacher's role is not to tell, because telling does not really work. The teacher's role is to orchestrate the opportunity to learn. And orchestrating an opportunity to learn takes several things. First of all, you have to design that opportunity. That's an engineering problem. It's a design problem. You have to decide, to do good engineering, you have to decide what your goals are. What is most important that these students 3 years later remember that they learned in your classroom? To think about that in planning your course, not just, this is the material I have to cover. What are the things that really need to be emphasized in the learning? And that was the question we were asked. But we can only guide a teacher so far. Every teacher has to rethink that as they design their course. Also worrying about the time. Of course, you only have a certain amount of time with these students, so you have to figure out how you can do the most important things you need to do in the time allowed. Then you have to apply the science. You can't engineer anything well without knowing what you're doing and knowing the science of what you're engineering. So you need to understand something about the science of learning. And you need to understand some things about how people learn, and particularly about how they learn the subject you're teaching. And then you have to put on the show, orchestrate the opportunities. And if you're doing learning where the students are actively engaged and talking with one another and participating in the process of developing their own ideas and making sense of phenomena for themselves, you have to be engaging. It's not stand-up comedy like giving a lecture. It's improvisational theater. You have to be responding and reacting to what's going on in that room in a way that makes sure that all students are having the opportunities you want them to have and participating effectively, that the conversation that the students are having around the table is about what they're trying to understand and not about what they did yesterday afternoon. And all of those things make teaching a really complicated job. And I have a great deal of respect for the people who do this job in the public schools, because the range of students that come into their classroom and the diversity of those students' backgrounds is something they also have to deal with and take into account as they do this job of planning and delivering effective education. So to teach well, you need not only to know the science, you need to know the science that goes along with teaching the subject, specific things. For example, if you're teaching introductory physics, it's very useful to understand what are the standard misconceptions which make it hard for students to learn the things you're telling them. What are the perceptions of the world, which are actually not misconceptions, they're real perceptions of how the world works. When you roll something across the floor, it stops, right? That's not a misperception. However, it doesn't seem to match what Newton's laws say. So children find that very confusing. And we have to understand what we're changing about their thinking and understand what opportunities to learn will help them change their thinking in order to teach any subject. You have to learn to interpret student questions. Student questions reveal student thinking. And knowing what the student is really wanting to ask rather than what they actually asked because they didn't know how to phrase the question the way you would have phrased it is an important part of the art of being able to respond in the moment to the student. And you don't necessarily answer, but to ask a question back which guides their thinking in the direction it needs to move. So many pieces to this job. It's not an easy job. I'm not saying we can do it without working, but it's such a critical job for the future of our country and for the children of our society, that taking the effort to do it well at whichever level we're doing it is something we need to invest more in. Okay, so what does the learning research tell us? It says that for learning that can be used. So people can learn to recite what you told them, and they never can use it anyplace else. They can learn to solve the problems that are standard problems the way you teach them to do it, and get A's in your courses, and still never be able to use that knowledge in their lives because they learned it in a way which was totally disconnected from their actual understanding of the world. So if you want learning that can be used, the students have to engage actively in the learning process so they change their conception of the world. Their models in their brain have to shift. And the only way you can do that is to make them make their thinking explicit and see how it contradicts what you're doing and actually engage in the work of making sense to be able to explain phenomena using the science ideas that they're learning. That's a very different kind of learning than happens in most science classrooms. And it requires a culture in the classroom that supports the students to do that. So the teacher has to manage the culture of the classroom as well as the activities and the kinds of things that students are doing. In a large class, giving a lecture is the easiest way to deal with 300 students. But those 300 students, if you videotaped the lecture and handed it to them, they could learn it a lot better because they would watch the lecture several times, and they would watch it in 10-minute segments, and they would go back and listen again when they didn't get something. And none of that can they do when you're giving the lecture in the classroom. So figuring out how to flip things around, so when they're together, you do something that takes advantage of them being together, and when they're separately working, you give them the resources that they need to learn the new material in a way that works for them. It's very different from saying, okay, I'll give the lecture and you figure out how to learn it. Because that's what we all did. We figured out how to learn what we heard. We listened to the lecture, and then we went outside the lecture and figured out what it was we just heard and how to use those ideas and understand them better. So the learning doesn't actually take place in the lecture. What takes place in the lecture is the hearing what you need to learn. And as I said before, it's very inefficient. A student who's a good note taker can perhaps keep the record and go back and learn it. But it does not work for the majority of students. And particularly today, for students who are used to information coming at them in a different way and in much smaller packages, packaging it up differently helps a lot. And laboratory. I'm hearing that laboratories at Berkeley are being revised, and that's great because they need to be. The standard laboratories that we've used for years in classes, research shows that students go in and they go through the motions, they follow the instructions, they write the lab report, but they don't think about it at all because it's just a recipe following activity. And the majority of students don't see the connection between what they're learning in the lecture and what they're doing in the lab, even when the instructor thought that lab supported that lecture. So figuring out how to make the time that students are spending in lecture, in lab, and in section add up effectively to better learning is something that has been done, can be done. It's not easy to do in large classes. It's much easier to do with smaller numbers of students. So there's a financial barrier to doing it in a university like this, which is a challenge. But there are some things you can do in the large lecture format. And one of them is just stop occasionally and ask people to talk to one another, to process what they've just learned. So now I want you to talk for 2 minutes. Literally, find a person near you and talk to them. What does the idea of active learning mean to you? What does it mean to learn actively? I've said this a little bit. We've got to make a laboratory active learning too, which means the students actually need to be doing a real investigation, not just following a set of steps that are pre-prescribed to get to a predetermined answer. And then they're learning what science is. Carl Wyman has some recent papers on this where he actually interviewed students after laboratories at a large range of universities and asked them what they were doing when they were doing the laboratory, and found that for most of them, the laboratory was not doing science, it was following the rules. So we need a chance, students need a chance to do science, and they need that earlier. They need it in K-12, and they need it as undergraduates. No, you don't have to wait till you're a graduate student before you can learn the joy of actually doing science and figuring things out. Now, a lot of people say, well, it worked for me, so why do we need to change it? And I say there are reasons that have to do with the fact it only worked for a few people, and we're the select few that it worked for, the ones who became professors of physics at universities like this. We learned in spite of, not because of, our teachers. The other thing is, the world has changed. And knowing numbers and facts is not nearly as valuable a skill as it used to be, because you can find them very, very quickly. You have to know concepts. You have to know contexts. You have to know big ideas. But learning all the details, that's for professionals. That's not for getting students interested in science in K-12. And we've spent too much time emphasizing a lot of details and too little time emphasizing the really major ideas that we think are important to be learned. And anyway, developing an ability to memorize or to rapidly do a standard set of problems really doesn't get you very far in the world today. Computers will do those standard problems much quicker than you will. And so and my phone remembers much better than I do. But learning to think and to figure things out, that's the key, and that's the important thing. And that's much harder to teach, but it's also much more valuable once learned. It's not dumbing down to teach different things, to emphasize different learning. People thought it was dumbing down when we stopped teaching Greek and Latin to all students. And in a sense, it is. We no longer can read ancient Greek, most of us. There may be one or two people in the room for whom that's not true. But in this world, the skills that count are not the ones that have been emphasized in standard K-12 education in science. And we need, and employers are crying. They say, we cannot find people who can do the kinds of tasks we want them to do. So we have to think, can we provide an education which not only prepares people for life better, but prepares them for employment better too? And I truly believe this message goes. So we cooked up, we invented a term. The term is three-dimensional learning. Science learning should be three-dimensional. What are the three dimensions? You have to engage in science and engineering practices. You have to do the things that scientists do. First of all, in order to understand what scientific knowledge is and how it's obtained, but also in order to really get the concepts you're learning and see how they apply, and therefore be able to use them later. You also have to learn a set of ideas which we called cross-cutting concepts. I'll come back later and tell you what the cross-cutting concepts are. That's the second dimension. They're tools for problem solving. And third, of course, you have to know some core ideas from the disciplines. You have to learn the basic science. And in K-12, we should be building a base so that in future, any individual can go further in any direction they want. So we have to build that base. So we expect students to be developing explanations in science and developing designs in engineering. And we put engineering with science because if it's not in science, it's nowhere in K-12. And it's a travesty today if a student graduates from high school and doesn't know what an engineer does or has never had the chance to design anything for themselves. So we figured engineering had to be there. And besides, it's another good way to learn science, to use your science to build something or design something. Not necessarily something you build. You might design a system for processing information through, I don't know what, but you design a plan of action. That's a design problem. And that when we say engineering in this context, we mean a very broad sense of engineering, any kind of design process that's producing a product or a process. Of course, when we say students are developing explanations, we don't mean that K-12 students are developing new science. It's very unlikely that they will do that. What we mean is they're taking the science that they're learning and using it to explain real-world phenomena that are introduced by the teacher, such that in order to explain that phenomena, you need that science that you're learning. Right, and an example I've used very often, I keep doing this because I can't see you, the way the lighting is. A railway tank car, steam cleaned and then closed. And an hour or two later, it implodes. Well, to understand why it implodes, you need to know something about phase change and about temperature dependence of the behavior of gases and about air pressure. And there's many science concepts that go into understanding that phenomenon. So producing that phenomenon is something kids need to explain. It's a pretty dramatic phenomenon, and they think they want to explain it. So now they're interested in hearing about phase change and air pressure and all of the things that they need to learn in order to explain it. So the phenomenon provides the context in which the learning is relevant and applicable. And choosing the phenomenon then is a critical part of designing the learning experience. And we expect students to be able to explain phenomena, not to develop science theories. But to explain phenomena, you go through the same kind of processes as you do to develop science theories. So all of the practices which scientists and engineers do are relevant. I think this model applies just as much at the undergraduate level. And I won't stress the terms here, but having the students work together to develop explanations of real-world phenomena is a wonderful way to make them want to learn the science that you're teaching. And the phenomena maybe not be things you can bring into the classroom directly, but you can bring them in with video and simulations and other ways of having them experience the phenomenon. So hands-on is not the center of this. Yes, you want students doing some hands-on investigative work, but it's the minds-on part that really matters. And when we look at the practices, you'll see that only a few of them have to do, only one of them actually has to do with planning and carrying out investigations, doing the experiments or observations. The first is asking questions. And in engineering, we differentiate. In engineering, part of the engineering cycle is really defining your problem, defining the constraints and goals of the process. It's also true in science, but scientists don't stress it as much. So we differentiate the science and the engineering there. Engineers certainly ask questions too. Developing and using models. Having students develop their own model to explain the phenomenon, modeling this process of the tank car and what was going on inside and outside the tank car that made it implode, helps the students bring their thinking into a visual form and make it explicit, and therefore they can see when it's not working and begin to change it. So the model, having the students develop their own models, not just use the models you tell them that scientists have developed, is important. Planning and carrying out investigations, clearly. Analyzing and interpreting data, we put that separately because students can also analyze and interpret data they didn't gather. And in the world today, there's lots of very interesting data out there that you can get access to and look at phenomena that you couldn't possibly bring into the classroom. But you can look at data about a hurricane and where's it going and where did it come from. There's lots of meteorological data, for example, that can come into the classroom and give students really deep thinking work, even though there's no hands-on piece to that lesson, but it still engages them. Of course, when you're doing the analyzing data, you're generally using mathematics, and that's put in there explicitly to say, as we're in K-12, we need to make the progression of the mathematics we're asking the students to use matching the progression of the mathematics they're learning. Constructing explanations, that's the goal in science, or in engineering, developing a design. And as you do it, as you develop an explanation, you have to use your model and the evidence to argue for your answer. So arguing from evidence, key skill, and then obtaining, evaluating, and communicating information. The critical word in there is evaluate. Yes, of course, students need to read and obtain information from videos and other sources, but they also need to communicate. But the skill we haven't taught is evaluating. When I can find lots of information on my phone. Some of it's good, some of it's not. How do I know? And what do I do to figure out what's reliable and what's not? That's a skill we need to be teaching because it's a critical skill for democracy, too. Okay, so I want you to talk again for 2 minutes. And the question you should be talking about, particularly if you're a university teacher, but also if you're teaching at any level. And if you're not teaching, then you can talk about other teachers you know about. When do students do these things? And should they? In your classrooms. I want to hear talk. You've got 2 minutes. Okay. So that's just dimension one, doing the practices of science. So another question you could discuss is, did we get the right list of scientists in the room? Are these all things that you do? And clearly, in different areas of science, different ones of those practices have different forms and different emphasis, but I think the list works pretty well across all the sciences. The second thing that works across all the sciences is this list of things we call cross-cutting concepts. These are ideas which every scientist uses, and traditionally we simply have forgotten to teach them. We think students learn them by osmosis. Like, science is about deciphering mechanisms of cause and effect. Or science looks at patterns and tries to find why those patterns happen. Or science thinks in terms of systems. Whatever problem or phenomenon you're looking at, you have to define what's the system involved. What are its components? How do they interact with one another? What's flowing into that system or out of it? And under what conditions is that system stable or unstable? So these 7 concepts are lenses for looking at a situation where you don't necessarily know much about it and figuring out what's going on. And any one of them can be used in many, many contexts. All of them have roles across all of science. So why not be explicit about it and tell the students, you know, it's really useful when you're looking at a problem to try and figure out what system is. What are the things that are engaging in this phenomenon? And what can you kind of ignore and put to the side and say it only enters through what it sends in or out across the boundary of the system? And that those boundaries are always artificial. I mean, I can talk about the human body and I have a kind of natural boundary at the skin, but clearly a human body cannot live with with only what's inside it. It needs things that are outside it too, and things come in and out all the time. And so thinking about how you define a system and how you define what you're going to focus on in detail and what you're going to put in the background is part of the way you make the problem solvable. And it's a skill that you can learn. So why not teach it? And so all of these cross-cutting concepts, that's the second set of things we want students doing, using these tools to try and explain phenomena. When they're given a problem, they should be given the tools to do it. And these are part of the tools. And then the third dimension is the concepts of the disciplines. So that's obvious. I don't have to make a list of them, although we did make lists to say these are the core concepts across physical sciences, life sciences, which includes ecology, earth and space sciences. And the fourth list we made was for something we called engineering, technology, and the applications of science. Because when you ask scientists what matters in their discipline, they actually never talk about the applications. They talk about the ideas as abstract ideas. But for many students, the fact that these ideas have applications in their lives is what makes the idea worth learning about. And so talking about the applications of science in society and in their lives is an important part of teaching science in a way that makes people want to learn it. And the engineering, right, we're asking kids to do engineering design. So if they're going to engage in the practices of engineering, they need to know some of the concepts of engineering. They need to know what is the way that engineers go through the cycle of design. And yes, it's iterative and recursive, but it has a set of well-defined steps. If you don't teach them the steps, they're not necessarily going to do as good a job as if they know how to go about that process. So there's core ideas around engineering design that is knowledge that kids are learning and developing across the years of K-12, just as there are core ideas around forces in motion in the physical sciences or the structure of matter. And in this case, in this game of giving students phenomena to make sense of, the role of the teacher is as the coach, the mentor, the questioner, making the discussion powerful by asking the right questions at the right times, not necessarily by giving the answers to the questions. And that's extremely frustrating for students who've learned that what I do in school is learn what the teacher tells me and give it back to them. When the teacher won't tell them and won't answer their question because they're supposed to figure it out themselves, the transition is actually hard for the teachers and the students because the students resist not being told. Why don't you just give me the answer? Okay, this is my diagram. It's a complicated diagram, but I want to talk about it a bit because for teachers to understand, this is the way science works, but it's also the way explaining phenomena work. Let's focus on the middle column. The middle column is the learner, or maybe a group of learners, starting from their prior knowledge, which they don't know much about whatever this phenomenon is they're being asked to look at, and finally getting to a model and an explanation where they think they can explain what's going on in this phenomenon. Well, they don't do it in a linear, straightforward process. They have to go back and look at the real world and look at the phenomenon, or at the videotape if they're looking at a phenomenon from a distance. They start initially just looking and wondering, and there's a process, an iterative process of moving between developing your ideas and going back and checking them by doing observations and eventually experiments in the real world, in the actual phenomenon. And on the other side, there's all the information and other people that can tell you things. So you can develop your ideas either by going and looking or by talking to other people, starting with peers in your class, later finding out more about what the experts know, and finally you have to communicate your own ideas back to the world. So this complicated back and forth looping process, and the practices of science are in the columns between the development of the knowledge and the real world, or the development of the knowledge and the knowledge resources outside the group of students doing this work. It's a very nonlinear process. Orchestrating this process is what science teaching should be, making this process happen in the classroom. Of course, there's an orchestrating that happens before you get into the classroom. What phenomenon are you going to present that the kids should be explaining in order that the science that you want them to learn becomes relevant and effective in developing an explanation? So, another short discussion. In these pictures, it was developing the model that was at the center. Why is the model the center of everything here? If I were to make a similar diagram for developing a design, it would look the same way. It would have the same iterative, recursive, going for information, going back to my actual real-world version of what it is I'm trying to solve. And so the process is not very different. That's another reason to put engineering and science together. If you look at the practices, engineers do all those practices too. So thinking of engineering and science as separate different disciplines, yes, they are, and they're different kinds of expertise, but they have a lot of overlaps. And so for efficiency in teaching, rather than making engineering another course that you teach one time separately, putting engineering as a piece of what students do as they're learning science seemed a very natural thing to do to us. And the other part about engineering is it's one of the places where students naturally learn that a failure is not a disaster. It's something you learn from and go on and get better. Nobody's design works right the first time, right? You always have to learn and try over. And that process of learning from failure is actually critical across all learning. And so emphasizing it in the engineering context is very helpful to have students recognize that mistakes are not deadly unless you just run away from them. Mistakes are what you learn from. All of this doing takes time. So the amount that you can teach in terms of core ideas and content, in terms of science that you know, seems to shrink. It's true and it's not true. The not true is, if you go into schools today, you see how much time is wasted repeating things year after year because they weren't well learned the first time, so we're going to teach them again next year. And we're going to put kids who graduated from high school in remedial courses and teach them the same thing again for 3 years and then not let them go to college. So doing things over because you didn't do them well is very time consuming. Doing it well and effectively, the students are learning to learn. And I had a third grade teacher say, it's amazing, the students are coming in and they're saying, I noticed this, and my observation is that, and I claim this, but I'm not sure because that, right? Well, these are third graders. They didn't make that up. They learned it in second grade because the teachers were having the students do this. And what turns out, children can think. We just don't give them opportunities to very often. And this way of teaching provides support for students developing confidence in their own ability to think things through, which I think is as important as any piece of science that they learn. And so taking the time to do this, rather than spending lots of time repetitively drilling so people will remember the terminology, or doing many copies of the same problem so you'll get quicker at it. It's a very different investment of time. And so we have to redesign curricula and redesign the way we think in order to get these different learning goals to be the ones that come to the fore. So I think we have to value learning to think over learning a lot of facts. And in general, the way we've taught science has been, you learn these facts today and those facts tomorrow and another set of facts the next year. And the student has no context in which to put those facts and no way to use them and remember them. This way of teaching science has been shown. More students get interested in science, more students begin to interact in a very positive way with the information and want to know more. So it does have an impact over time that finishes up with more learning happening and a more effective kind of learning. So I keep preaching this. You have to try it to find it out. But it's very important to do that. Now at the college level, it's really the same story, right? We want students come in and they have various levels of preparation and there are various things you want them to learn. But thinking through the goals of the course in terms of what you want them to be able to do and to be able to use what they're learning for makes you rethink what you emphasize and what you spend time on and how carefully you build their capabilities as well as their knowledge. So there's a lot of research done, which is called discipline-based education research, done in college classrooms. And it comes up with the same kind of conclusion, that when you do active learning in college classrooms, it's not that a few students get better. The whole distribution of student understanding of the concepts of the subject moves up. So more students get to the top level, but also the students who weren't getting anywhere get somewhere. So it really is worth the time investment, even at the college level. But as I said before, in a large lecture hall, all of this flipped classroom is much harder to do because the geography of the lecture hall doesn't make it easy. Now, you can do things like I did. You can take 10-minute segments and have time to talk so the students get to process the knowledge. That's a first step. There are other things you can do, like having teaching assistants who are students. Actually, the term is invented at University of Colorado. They call them learning assistants because they're not supposed to be teaching. They're supposed to be supporting learning. And they work, they're students who took the course the year before. And they're there to ask the questions. When you're doing your little group discussion, there's an extra person there who can help the group have a discussion that moves in constructive directions because they're asking the right questions. And those students also gain because, as anybody who teaches knows, when you start teaching, you learn much more about the subject than you learned when you first learned it. So the learning assistants actually become much more competent in the course they took the year before by being the learning assistant. And at the same time, they're supporting the learning of the students this year. So that's a model, and you can do that even in a large lecture hall. It's not as geographically convenient to have 6 kids talking to one another with the learning assistant in a big lecture hall, but you can arrange it so that it can work. So there are things you can do. Of course, the ideal is to go further and redesign how you use your teaching resources and the space so that you really can have active learning and group work effectively in your classrooms. And the model, it seems to be probably about 60 students can be handled in a single room teaching this way with the right equipment and facilities. The space looks different. It's a room with multiple tables, not a lecture hall. And the role of the students and the teacher changes. This is an investment. And as you move up through your courses, more and more of the courses should be in this format because they are smaller numbers of students anyway. But thinking about how to move step by step towards a situation where you don't see students asleep in the back of the room, because they can't be, because of the things they need to do in that classroom, is an important piece of making learning work better and for more students. A lot of people talk about how technology can facilitate learning. Well, technology, like anything, can be used well or badly. It's a tool. It can be used to support learning. It can be used in deadly boring ways too. So figuring out what technology to use and how to use it. Simulations, for example, are a very powerful tool in physics learning. Using good programs that allow students to manage and manipulate data. That's what CODAP is. It's called the Common Online Data Analysis Program. If you have data in CSV file, you can put it in CODAP and you can play with it. Sage Modeler is another tool which allows students to build cause and effect models of systems. And so there's tools out there that are very, very powerful. Finding those tools takes time. So again, curriculum design is a process which we shouldn't have every teacher doing individually, but some support that tells them, and this course at this year, these tools would be particularly useful. And here they are. So you can bring those. A lot of teachers have discovered and used the fetcolorado.edu. Probably physics teachers here use them some too. The physics simulations, many short. Also chemistry. I think now there's biology as well. So they're a resource. Once you find it and start using it, you realize how powerful it can be. And so technology is not an answer, but it is and can be a big support. One of the big challenges, when we come out with a new way of teaching science, and 30, I think it's almost 40 states now adopt some, there's a lot more work to be done. Because the adoption is just the first step. You say, these are my standards. Okay, now we have to change the textbooks. Now we have to change the way the teachers are prepared. Now we have to change the tests we're giving to see if students are learning, because if we want them to learn different things, we have to use different tests. And all of that work is ongoing work, and its pieces are beginning to appear, but there's lots still to be done, which is why I still spend my time engaged with various bits and pieces of this work. But one of the things I think we need to do is we need to change our elementary school model. So we begin to have specialist teachers earlier. Because unfortunately, we have too many teachers teaching math and teaching science who don't like math or don't like science. And the first thing they communicate to kids is, this subject is not interesting. So figuring out how to change the way we do school it's political and it's resource intensive, because we have the teachers we have. How do we change the way we use them? Well, that depends on which teachers. Could we just say, okay, we'll make half of the teachers math and science teachers and half of the teachers language arts and history teachers? No, that wouldn't work, because they don't fall into those two halves. So it's not a change you can make all at once, but over time, I think we should look towards some somewhat different models of how we organize school and schooling that use human resources better. And I think I'll stop there and let you ask me questions. Thank you.
Thank you, Helen. Do we have a few questions? Yes. Please.
Thank you. Thank you for your talk. And well, the question I have is related to an issue that I am struggling with my own research. So I wanted to know, what are your thoughts around it? So I wanted to know what are your perspectives on the role of culture in the teaching of science? Specifically, what comes to mind are communities that might have epistemologies that are different from the Western one. For instance, indigenous communities in Ecuador.
Absolutely. This is one of the challenges teachers in the United States have, that they have children in their classrooms coming from many different homes with many different cultures. And the teachers are told, you should make your lessons relevant to your students. Well, what's relevant to one student is not necessarily relevant to the other. So first, critical is that the culture of the classroom welcomes all cultures, right? And makes all the students feel safe and belonging in that classroom. That's the first condition for learning. You can't learn where you don't feel welcome and you don't feel safe. So that's step one, step zero, right? It has to be. But beyond that, thinking about how you vary the things you bring in, and also when you're developing, so you have to develop the culture of discourse in the classroom, no matter what homes the children come from. They don't have a culture of scientific discourse in their homes, with very few exceptions, right? I mean, my kids maybe grew up with 2 physicists for parents. They had more scientific discourse than the average kid, but still, you need to learn, this is the way we talk science. And this is the way you disagree. You don't say, nah, you're wrong. You say, I disagree because. And even in many teachers say, the kids have to say, I respectfully disagree because. But teaching how, developing a culture and being clear that this culture is the culture of this classroom, and it's not that your culture is wrong or your culture is wrong, but this is the way we do it in science. It makes it a safe space for kids who come, but then also recognizing that some kids will speak up because they come from a culture where speaking up is accepted, and other kids won't because come from a culture where it's not accepted. And that also has to be mediated by the teacher. So the teacher really has to be an expert in many things, not just science teaching, but developing the culture where that discussion among the kids can happen and happen in a way that all of the kids want to engage in it and feel that they're welcome to engage in it is a big piece of the work.
I think we have to remember that students are human. And some truths are inconvenient truths. And just as one example, wild animals don't like having humans around. We don't want to face that fact, usually. So how do you teach inconvenient truth?
I think what's inconvenient to one person is not necessarily inconvenient to another. But first of all, we don't teach science as a system of belief. I think scientists should never say, scientists believe that, right? Because science is not about belief, it's about the weight of the evidence. And what you say, the evidence supports the conclusion that. You don't say, scientists believe that. So not setting up science as a belief system, but setting it up as a way of looking at the world and finding out things about the world is the first step. So then you can say, well, it may be that you would love to be out there in the wild with all the wild animals. But the research that we've done says that the wild animals avoid the places where the people are. So clearly we can conclude that the wild animals don't like being with the people, and that we should leave some space for them to be. So you can make that argument in the context of, it's not that you're wrong to like to be with the wild animals. It's that the evidence says the wild animals don't like being with you, right? So, but always arguing, this is what the evidence says, not this is my opinion versus your opinion.
Hi, Dr. Quinn. I'm a 6th grade science teacher. and we've been using the NGSS in our classroom for about 2 to 3 years now. And this past summer, I did a grant studying design thinking at Stanford, and then brought design thinking labs back into my classroom.
Beautiful.
And had trouble convincing my colleagues, the other science teachers, to use them. And I was all for it, and they just couldn't get on board with engineering in the classroom. So I kind of wanted to hear your thoughts on that. And then also, you talked about describing phenomena, and I kind of run into the problem of magic is science is magic, and that we did something and it was fun, and that's all they remember, and they don't make the leap to the connections behind the magic.
Yeah, that's what very often physicists love demonstrations which are gee whiz, right? Something magic happened. I think the choice of phenomenon and the phenomenon which is at the right level, so those students at that level of understanding, and with the science we're teaching them right now, can actually understand what's going on in that phenomenon. It restricts your choices. But to choose a phenomenon where it's just something magic happened is not going to support science learning at all. So it's critical that you pick a phenomenon at just the right level. And that's a curriculum design issue. As good NGSS-aligned curriculum materials begin to appear, more and more of that work has been done for you, and it's easier to find the right things. It's very easy to think a phenomenon will work to teach something, and then to find when you get down to it, the other things you have to understand about that phenomenon before you can get to the piece of science you wanted to teach really block the learning you wanted. So the figuring out which phenomenon and how to introduce phenomena effectively is a critical piece of curriculum design. Engineering is just another set of project-based learning, right? So you're doing project-based science learning, and the project is an engineering design project. Teachers will resist it if they don't see where the science is. And all too often, kids are given projects as engineering design, which are really just trial and error experiment, right? Here's some stuff, build and you're going to drop the egg and find some way to protect the egg. And you never ask, well, what science principle did you use in your design, right? How come this design worked and that one didn't? What was the physics of that, right? So making engineering design a science learning activity means you have to, again, choose those design projects and it can be an egg drop. There's nothing wrong with an egg drop as long as the project is designed so the students have to explain their choices, right? And before they drop the egg, they have to tell you why they made the choices they made. And after they drop the egg, if the egg broke, they have to explain why it failed so that they can build a better one next time, right? So there's ways of doing the engineering project that don't have very much learning in them. And there's ways of doing that. There's the same project with a much more learning.
My understanding is that math is a real gateway for students in many fields. Maybe in middle school, we focus on algebra, for example, in 8th grade. So if math is a gateway to science, maybe to other success in education, are the techniques you talk about in terms of active learning relevant to the mathematical training? And it seems like it's a slightly different...
It's different, and the techniques are different. But again, the mantra of active learning certainly applies. So if you look at mathematics standards today, they talk about mathematical practices, right? And they talk about having the students engage in problem solving where they have to come up with more than one way of solving a problem. And thinking about mathematics conceptually is much more built into the modern math standards than it was, at least when I was learning elementary school math, where it was all about getting the numbers right. And again, in math learning, one of the kids say, I'm good at math or I'm not good at math based on how fast they are at math, because that's the way the tests work. If you can do 100 problems in a certain time, then you're good at math. And if you can only do 75, well, you're not so good. Well, maybe you actually have the concept just as well. You're just slower with the manipulation of the numbers. And mathematics is not just numbers, right? So how we teach and what we emphasize, again, in math, what we've done and what is changing is similar to this. It's not the same, but there's a similar story for math education. Yes.
I know we have many more questions, but I think we have time for just one last one.
Oh, if I may, thank you very much for this wonderful lecture. I teach a large class of introductory physics. So I have a question at the high end and at the low end. At the high end, my students, many of them are biology majors trying to go into medical school. And so I have to teach something that they may encounter on the MCAT test.
No, you don't.
I don't?
When I
Well, it
taught
seems
pre-med
like I do.
physics,
Yeah.
I said, look, and I don't think it's changed very much. The MCAT test, if you can read an equation and plug in the numbers and interpret which is the M and which is the W or whatever in that equation, you can do well on MCAT tests. So I say there's not a lot of science you have to know to do that test. You have to be able to interpret words into equations and plug in and solve those equations.
Right.
And that's a very limited set of skills.
Yeah, but they have to.
They have
sort
to
of
do it.
Have encountered a dipole, for example, or something like that. So anyhow, I would just add to your list of things that have to change. Maybe we should talk to the MCAT people.
Well,
and
actually the tests are changing in medicine.
That's good.
And there is considerable discussion about what are the skills we need for students entering medical school and
Right.
how. And physicists may be horrified because they may drop physics altogether.
And the
But
other, if I may,
I
on the
think
other. Sorry.
but it's part of the same discussion. Standardized tests have evolved, and it started when we started to have computers, right? And then it became very cheap and very easy to ask a lot of short questions. And a lot of testing moved to how well can you do on that kind of test? But the test isn't always testing the things that really matter for becoming a doctor.
Or the
Or for
concepts.
becoming a physicist or a chemist or whatever else. So figuring out how to test the things I'm talking about, the things that matter, being able to solve a problem when you meet a problem that's not the one you met in the classroom, looks similar but somewhat different, and take your knowledge and use it there, that's a different set of skills. Unfortunately, you can't test it quickly, right? You have to give somebody a problem and let them solve it. So it takes time. And therefore, you can't ask as many questions, and statistically, you can't get as reliable a measure of the student's capability.
Right.
And so that's the nature of the situation. We have to push back against valuing statistical reliability over valuing the question the skill that's being tested.
Right.
Let's thank Helen for a wonderful talk.